first of all. The schedule has changed. If you go to Canvas, you can see the new updated schedule. And I realize I need more time teaching you support vector machine and neural networks. And the assignments, the 2 remaining assignments now have 2 weeks for you to complete, right? And what else? The exam, probably I'll have 3 questions at max. But yeah, let's see if that changes your distribution of numbers. Okay. And yes, so the midterm, unfortunately, will be happening after the Thanksgiving break because we are yet to cover a lot of contents. And I just need more time because of my travel and all that, so I needed to make this adjustment. And this gives you more time in terms of reading, doing the assignments, getting better prepared. I don't know how many of you actually seriously study during the Thanksgiving, but if you choose to, you can. Okay? All right. So we're going to start support vector machines today. I think I have been mentioning this name for a while. We haven't really got a chance to talk about it, so today is the time. And previously we have been talking a lot about perceptron, and we will start from that because support vector machines actually started from the limitations of perceptron. Okay? So from the perceptron, we kind of learned something. First of all, if you have a large margin, then the number of mistakes perceptron will make goes smaller, right? Because you have this R divided by gamma square formula. So you can find a plane pretty easily if there is a large margin. And large margin can help prevent overfitting, and even for sufficiently large margin, there is a paper that kind of shows like you don't even need R square, R by gamma square. It's just a linear function of R by gamma, number of data that you need actually to make improvement. Well, that's not, covered. It's not part of our lecture or in the syllabus, but it's good to know. And then we already know like maximizing the margin is something that is good because we want a classifier that maximally separates the 2 classes. In perceptron, we knew that it will guarantee some partitioning given that there is one that exists that clearly separates the data. But it doesn't guarantee the maximum margin. Support vector machine, on the other hand, is actually trying to maximize the margin. It's not that it will just give you any classifier. It will give you the maximum margin classifier. So we will find a plane that not only separates the 2 classes purely, but also it will maximize the margin. It will choose a plane that maximizes the margin between 2 different classes. Still, we are assuming data is linearly separable. Why? Because we have learned kernel trick where if we can do the linearly separable case, then we can apply the kernel trick to actually make it transform to another space where most likely it is linearly separable. So let's start with the linearly separable case and derive the formula for SVM. And once we go to some place where we have a dot product, we can replace that with a what was the lecture topic in the last class? Kernel function, right? Once we have a dot product of 2 points, we can replace that with a kernel function, and then it will be non-linear and in a high dimensional space where it will be probably, hopefully, linearly separable. It's not guaranteed, but we will also handle cases where it's not guaranteed. We'll show all the cases one by one, but let's start with the linearly separable case, but looking for a maximum margin. So see the difference? For perceptron, we also looked for a linearly separable case, purely divided data. Here we are also doing that, but in perceptron, we were just fine with any plane that divides it. But now, we are not fine with any plane that divides it. We want the maximum margin classifier. That's what we are going to cover. Any question before I start? Good. Okay, you have seen this slide many times. This is what is the definition of a point, of the margin of a point with respect to a plane. And then we have seen this definition again many times, where you have a set of points, and with respect to a particular margin, what is the smallest margin is actually the margin of a set of points. And then we also have seen, if we don't define any particular W, then whatever W maximizes that minimum margin is actually the margin of the whole set of points without any specification, right? So we know all these definitions. We will be using all these definitions again. So our definition of margin still remains the same. The gamma is a set, for a set of example S, is the maximum gamma W over all the linear separators. So we are basically looking for a W that maximizes gamma, right? That's our definition. Okay, so what is our input and output? So let's first define the problem. We'll go to the solution later. So our input, which is not realistic at this moment, assumes that you know gamma. Do we really know gamma, given a set of points, without any analysis? We don't, right? I mean, we don't know what is the maximum separation between two classes. There may not be a separation at all. It may be like non-separable. But let's start with something simple, and we will eliminate these assumptions one at a time. So we assume that we know the gamma that we are looking to maximize. The value we know. So gamma is given. And the set of points are given. So what is S? So normally, usually, the points are actually given, right? I mean, this is not good. You know there are some positive classes, there are some negative classes, right? Subpoints. And this is always given. Now we are trying to learn a classifier, right? Learn a plane. So S is essentially these points. So S is a set of points, x1 with the label y1, x2 with the label y2, and so on. So S is the set of all these points. That is what is usually given, like this is your data. Now learn a plane. But there is one additional input which is unrealistic, but that simplifies our life for now, which is gamma. So we know the maximum separation we can achieve between these two sets of points, two classes, is actually gamma. Okay? That's our definition. That's our input. Now, our goal is to find this plane. We don't know this plane. We just know the gamma. But our goal is to find this plane, and the way we define this plane is how? How are we defining planes? By the orthogonal vector, right? Orthogonal unit vector. So we actually define a W, which is a unit vector, W equals to 1, and which is perpendicular to the actual decision plane, right? That's what we need to figure out. And also we need that vector to be a unit vector. Why? Because that's how we define margin. That's our definition of margin. Remember? When we defined margin, if we go back here, you see? So x dot W, here the definition of margin comes from the fact that W is a unit vector, and you are taking x dot W, which is a unit vector in the direction of W. So you need, by definition of margin, W is a unit vector. Okay? So you want to find a plane W that is a unit vector. That means the square is also unit, right? And I will come to the point y squared, because that makes our life even simpler. Because square functions are easier to optimize. They are convex. But the whole point is, unit vectors, their magnitude is 1, their square is also 1, right? So we need to find a vector where this is true, W, and it properly classifies all the examples with the margin of gamma. What does that mean? That means for all the points we have here, we should, for all I, we should be able to have W dot xi should be greater than equals to gamma. What does this mean? Yes.
The margin for a specific point in S is y sub I times W times x sub I. And you want to make sure that the margin for that specific point is bigger than. Oh wait, no, I think I got it wrong. Okay, sorry.
Anybody else? What does this really mean? Where is it coming from? What does it tell about W? Because we're trying to figure out W. W should be such that it's a unit vector by definition, and W does what? W separates the different xy points of different classes with a margin at least greater than equals to gamma. Complicated? Think about this. In perceptron, what we did, W dot x is less than 0. What was the label? Negative. W dot x greater than 0 equals to 0. What was the label? Positive. What does this mean? So this label, now if I combine both formula, that basically means perceptron was making sure that this positive or negative, whatever sign is, if we multiply that with W dot x, should always be greater than equals to 0. Right? I mean, if you have a negative point, that means yi is equals to minus 1. Right? And here yi equals to plus 1. That means if you multiply W dot x with the yi, everything becomes positive, right? Because W dot x should be negative for negative points. W dot x should be positive for positive points. So now if we multiply yi, if it's positive, then this positive remains positive. Negative remains negative. Is that clear? Okay. So now instead of this 0, we are saying we are not happy with 0. We want a gamma. That's what we are saying. It's not enough to say, to have a plane and saying like, oh, there is a positive here, there is a negative here. No, that's not good. I need a plane where the positive and the closest positive and negative are at least gamma distance away. That's what we are saying from the decision plane. So if I multiply a negative point with W dot xi, that should be greater than equals to gamma, where gamma is greater than equals to 0. It's a positive. And if xi is a negative point, that means yi equals to minus 1, then minus 1 times a minus number still should be greater than a positive value of gamma. Question on this? Yes?
Is that like a parameter that you set, gamma, where you decide I want this minimum separation?
Yes, for this formulation, this is what you want. But then you don't even know gamma. Then you have to search for all possible gamma. You need to find out that gamma as well. But right now, we simplified our life. We also don't know gamma. We need to figure out all of this. So from here, what we need to figure out, tell me what we don't know. Do we know S? Do we know S? Yes. Do we know gamma? No. Do we know W? No. Okay? So we need to figure out what is W and what is gamma. Right? Clear? From here, that's what we need to know. Okay. So that basically means we can slightly reformulate this problem. So if we don't know gamma, then our input is just the set of points, S. Now we are coming to a more realistic formulation. We don't know gamma, just S. Now we need to find some W and maximum gamma, because just one gamma is not enough. We need to find the maximum gamma that actually satisfies this. That W square, W is a unit vector, and if you take a dot product times the label, the sign of the data point, that should be greater than or equals to gamma. Right? So again, you need to find two things. One is a W that is a unit vector, and you need to find a gamma and the maximum gamma, so that this W taken a dot product with xi, yi should give you a value that is greater than or equals to gamma. Any question on this? Yes?
I think I'm a little confused on what x1, y1 is. Like, is x1 a positive and y1 a negative?
No, x1 is a data point. It can be a vector. x1 is a vector. It can be 100-dimensional vector. y1 is the label. Y can be either +1 or -1. That's the label. Y is the label. Think about perceptron. Y was +1 or -1, right? So it's still the same. So x is your data points. Y are their labels. So y basically means positive or negative. X are your, here is a 2D plane, that's why you see 2D points, but it could be more. So our output should be a W that maximizes this margin over S, and with the constraint that the gamma we find out is actually the maximum one that satisfies this. So that's a tricky problem, right? I mean, you have two unknowns, you have some constraint on both the unknowns, and you need to figure out both of them from the data. That's a hard problem. Okay. So okay. So yeah. And actually, let me switch to presenter view. That helps me. Yeah. What is coming next, right? So now, how do we solve this? How about we get rid of one of them? That would be cool, right? If I don't need to know both, figure out both W and gamma, let's say. I just want to figure out one of them. That would be nice. Do you agree? I mean, that will simplify our life, right? Okay, sure. So but before that, let me try to first tell you why we would even want to do that. Because if we want to maximize gamma under this constraint that we have a W that is unit, and that taken dot product with the xi yi gives you a separation of at least gamma. We need to solve this is like a constraint satisfaction problem, and we could use techniques like linear programming, right? Some optimization tools to solve it, right? We have seen, how many of you have taken some sort of background or courses in optimization? Linear algebra. Was there an optimization chapter there in linear algebra? No. Kind of. Okay. Really? Okay. How many of you have heard about linear programming? Okay. So, this, first of all, this is an optimization problem. You understand that, right? You have some goals to achieve. You want to maximize or optimize gamma. Here the optimization is maximization, right? We want to maximize the margin. Okay? That's our optimization problem with some constraint. You see? What are the constraints? You want to maximize gamma with some constraint. What is that?
And all the values are greater than gamma?
All the values, the second one. What is the first one?
Oh. That's a unit vector.
That's a unit vector, right? These are the two constraints. So these are called constraint optimization. And this function that you see, just use your intuition, like maximizing gamma. What kind of optimization does it feel like? Is it a linear optimization, quadratic optimization? What kind of function is it? Gamma? Linear, right? It's just a single variable like x, maximize x with some constraint. So it's a linear optimization problem. So you can use actually linear programming techniques. That there is a bunch of literature that is part of the optimization course. Unfortunately, we cannot cover here. I mean, we are already behind our schedule. But all you need to know, there is a linear optimization problem that you go back to your statistics optimization class and take the methods of linear programming and plug them in. But there is one problem. In linear programming, all the constraints have to be linear. So if you want to plug and play one of the linear programming, your objective function has to be linear. The first one, which is actually linear, and your constraint also has to be linear. Do we have linear constraints? Why not? There is a square. Okay, we have a problem, right? So linear programming techniques are not going to work because of this nonlinear constraint. So which one we want to get rid of?
W, so we can do linear constraints.
Yeah, W squared is the problem, so let's get rid of that. That's the idea. Okay? So it looks like we could use linear programming, but the constraints has to be linear, which is not true in our case. We cannot use that. So linear programming is not able to help us here. All right. It turns out, I mean, it's just not just only non-linear, it's also non-convex. It's like a circle, right? The square function, L2 norm, is basically a circle. So it's even harder. Okay. So what else can we do? We try to get rid of W, and we will do a very like heuristic trick to do this. Let's try to see what we can do. So we have two constraints. One is W square should be 1, And the other constraint is yi, w, xi should be greater than or equals to gamma. These are the two problems, right? There is another problem. We also don't know gamma. We want to maximize gamma, but we have no idea what is that maximum value, right? I mean, that's our goal. So what we can try to do is to divide both sides of this equation by gamma. Okay? Divide both sides by gamma. That makes it 1. How does that help? Well, so let's define this term as W. What is it called? W dash? W prime, okay. So let's define this term as this. Right? So now we get rid of this term. We are defining this by W prime, right? Do we need W prime to be 1? I mean, by definition, it's not 1. I mean, gamma is greater than 0. I mean, we want it greater than 1, essentially. So W prime is not going to be a unit vector. So we are not dealing with any W anymore. We are dealing with W prime. So we don't care whether W is unit or not. We don't have this constraint anymore. But we still have this maximize gamma. This is our goal. Now let's do a trick. One more trick. If we take a square here, and a gamma square, what is the value of W square? That was our unit vector, that was 1. So maximizing gamma is actually minimizing W prime, right? And we want the square because that makes our life easier, because square functions are even easier to optimize. So instead of maximizing gamma, we want to minimize W prime square. What is good about this? The good thing about this is we don't have gamma anymore. Gamma is gone. By minimizing this, we are implicitly maximizing gamma by definition. And we also don't have a constraint that requires a unit vector. W prime could be anything. Okay? Now, this is our objective function, and this is the only constraint we have. So again, we have an optimization problem. And what kind of optimization problem is this? Is this linear? Is this quadratic? Polynomial? Exponential? Which one?
Quadratic.
It's quadratic. It's a square. So now you can again go back to the literature of optimization And there is an optimization technique. There is a huge bunch of techniques that does quadratic optimization. And there also, you need constraints to be linear, which is fine here. So now you can actually take a tool and optimize this. Okay? All we need to do is to use quadratic programming techniques by framing our problem like this. And we throw it to the optimizer, the solver, and it will give you the solution. Okay? So that's what we have shown here. Instead of that problem, the maximization problem now becomes a minimization problem because they are inversely proportional. W star square is equal to 1 divided by gamma square. Inversely proportional. So now it's a minimization problem with just one constraint. And we can go to quadratic programming techniques to actually solve them. Because now we have an objective function that is convex. Like it's quadratic, right? That's a convex function we already know. We love them. All constraints are linear. We don't have any non-linear constraint like W has to be a unit vector. Because right now we have W prime. Remember, you see W here, but this W is actually the W prime because it doesn't matter anymore. You could call it X, you could call it Hugh, you could call it Matthew. It doesn't matter. Right? It's just a variable. So the W prime is again like written as just W to simplify our life. It's just a variable. But this W is implicitly actually meaning that W prime, which doesn't need to be 1. Does that confuse you? I mean, you are just replacing variable X with Y. You often do that with coding assignments, don't you? No? It's the same thing. Okay, all constraints are linear. That is true. And now we can solve it in polynomial time using standard quadratic programming software. What kind of techniques are we talking about? Well, maybe you don't know them and it doesn't matter because that's not the focus or the scope of this course. This course is about machine learning, and then the optimization theories that is covered should be covered by the optimization literature or class. And that is one option to learn, that is to go for an advanced machine learning course or go to a statistics department optimization course. Okay? But here are some techniques that the statistics class can teach you. Interior point, active set, augmented Lagrangian, conjugate gradient. These are all different methods of quadratic programming. You can use these tools to actually solve this optimization problem. Okay? All right? But we are not going to stop here. We will show you one gradient descent which we computer scientists like, you can actually implement. Because this is not very efficient. Can you tell me why? Why is it not efficient? Yes.
So because we have to like compute the gradient at every like point.
We are not even computing gradient here, but yes, I mean your direction is correct. Like look at that constraint, and you have to satisfy that every point. So you kind of like, as you try to find out W, you have to like check whether this constraint is being satisfied or not every time. All right. But there is another problem with this that we haven't yet addressed. What is that? What have we assumed about the data? Yes. It is still linearly separable. That's what we assumed, right? And most likely that is not true with your data. So all the trouble we have done is just to get a maximum margin plane, given that the data is actually separable and there is a maximum margin. Indeed. What if we don't have one? Data is not linearly separable. We are not talking about, one way is to do kernel function and hope that in the phi space they are linearly separable, but there is no guarantee. In the phi space still it could be non-separable. So even if we do kernel, we need to guarantee handle cases where it's not linearly separable, right? In that case, if it is not linearly separable, can we satisfy this constraint always? It is basically saying W, Y, I, Xi should be greater than or equals to gamma. Think about the previous one. We divided by gamma and introduced W prime, but the original thing was this dot product has to be greater than or equals to gamma, which is the margin. But there is no margin like gamma. Gamma doesn't exist. By definition, gamma should be greater than or equals to 0, right? There is a margin. But if that is not true, then can we satisfy this? No. So this constraint cannot be satisfied if the data is not linearly separable. So we have to come up with some other constraint. So this is kind of like a hard constraint we are talking about, right? It has to be greater than or equals to 1. I'm not going to negotiate. This is the hard constraint. But can we think of something like a soft constraint? Think about it.
You could just take the minimum if yeah. Sorry, I'm trying to.
Okay, we will find some cases where this is less than 1. What we want for that number to be?
As close to
1
possible.
as possible, right? Is that true? Can we write something like this? Minus this, where this is greater than or equals to 0, and we want to minimize this as well. Because if this is, with this constraint, if this is, what is the minimum value this can take? 0. If this is 0, we go back to the original formula. That's the best case. But if we cannot do it, we'll try to minimize this to the best extent we can, so that our errors that we are making are minimal. We will find a plane where we will classify most of the instances correctly, and we'll make some mistakes, but the mistakes that we make should be close to the boundary. They should not be far away. Yes?
Does that only care about like the worst error, like out of all of them?
It is trying to minimize the worst error, yes.
Okay.
Yes. Right? So the whole point is, our goal is right now not just minimize this, but also minimize number of misclassification. Right? Because we know it's not linearly separable. There will be some misclassification. We want to minimize the number. But this number is hard to optimize. There is no closed form solution. So instead of this number, we have this slack variable. These epsilon kind of symbols are called slack variables, and we want to minimize each of these slack variables, because if all of them are 0, we are good. That's a perfect separation. So instead of number of misclassification, which doesn't have a closed form like equation, we could now say we want to, for all the i's, we want to minimize this epsilon I, the slack variables. So we have two components in the minimization function now. We have to minimize the W square, and we have to minimize the slack variables, with the constraint that slack variables are greater than or equals to 0, and the weights we are learning, this W, is actually giving you a separation by 1 minus the slack variable. Okay? So this is what we introduce. Instead of that, instead of minimizing W square or W prime, whatever we define, it's just a notational thing. We are trying to minimize W square plus all these slack variables for each point, right? Each point will have a slack variable. You have x, y, I is the index of your data set. And this C is just a constant that gives you a weight between how much you want to optimize for this versus this, which one is more important to you. So C is just a constant. Is this formulation clear? This definition? So now you don't need a linear, yes?
So how is the slack variable computed? Is that just the distance between?
How is the slack variable computed? That's what we are going to cover.
Okay.
I mean, we have 2 more lectures for support vector machine. If you go back to the sketching, it's a long slide. Okay, and that will be the point of what I'm going to talk about next. But is the problem formulation clear right now? And you can still use, this is still a quadratic function, right? Is that true or not? Is that still a quadratic function, or is that now a linear function? It's a high school math question. What is that? It's still quadratic, right? You have the square function. Okay. Are these constraints linear or not? Are these linear constraints or not? What is non-linear about it? That's true? The constraints?
Oh, sorry, okay.
I mean, the objective function is a square, but the constraints.
Okay, no.
Now, so now we satisfy the requirement of a quadratic programming technique. If you formulate this problem this way and just throw it to the quadratic programming solver, it will give you a solution. Maybe it's not efficient, but it will give you the answer. Using one of those techniques that I just mentioned, the names you saw. Okay? Is this getting too complicated? Because things will get more complicated from now onward. How many of you don't know or don't understand what this means, given this input, this optimization problem? How many of you don't know? You do? Yes?
Why, like, if these points are, like, not linearly separable, why do we want to at least try to make a like a linear separator? Why not like a separator that's like that's a different shape? Why are we wanting to make it linear? Like what makes
Excellent
that
question.
benefit?
Why are we trying to even assume that W is just a plane? Why it cannot be something that is non-linear? It can be. It can be. Right now, we are just learning the simplest one, the linear. And there are non-linear solutions as well. And once you do the kernel trick, this same formula becomes non-linear. Because now you're transforming that into a different space. So in this space, in the phi space, that is non-linear. So that is linear. But in this original space, data space, that is non-linear. So if you just do whatever you are doing, if you just plug in the kernel trick, this problem itself will become non-linear. You don't have to do anything else. That's the beauty of kernel functions. Okay? But there is always a but. What do we need in order to plug in a kernel function? What is the condition?
We need a feed to do it, right?
We need a what?
Like I forgot the name.
What is the definition of kernel function? When we define kernel kxy,
Isn't it just a linear transformation? Like
kernel is not a linear transformation, no.
Function you can represent with dot products.
With dot products, a function, whenever you have a dot product x and y, you can replace that with the k of x and y to make it non-linear with a kernel function. So you need a dot product, right? You do. And we have dot products here. Right? So you can do nonlinear with this. Okay, so let's first finish the linear part, and then we'll talk more about non-linearity, right? And in the neural network, that's what we will do. We will frame everything as a general nonlinear problem. All right, so now, okay, so I have covered this. These are slack variables, and so the point is, how does this loss function actually look? Because if we made a wrong error, I mean, if we go back to the previous function, like if we talked about, my loss function is w square plus number of misclassification, right? So how does this part of the loss function actually look? This function actually looks like this. Right? What is this x-axis? This is yi dot w dot xi. What this value should be in order to do a correct classification. What do we expect this function to be? So that our classifier is correct. Greater than?
Equal to gamma?
That is good. That is even better. But what is the minimum that we need?
1.
That is even better than something
Greater than equal to 0.
greater than equals to 0. As long as we have a positive with this dot product, that's a positive class, we are predicting, that's a correct prediction. Maybe it doesn't have a large margin, just greater than 0. But still, that's a correct classification. So if we get something greater than equals to 0, we are doing good. We are only doing bad if it is less than 0, right? So if this is greater than 0, there is no loss, 0. But if it is less than 0, then we have one misclassification. That is 1. So that's a 0, 1 loss function. And if you count the number of this function, it will add 1 every time there is a misclassification. And that is the number of misclassification thing. But the problem with this is, this function is not differentiable, right? It's not continuous. And that's why we introduce those slack variables, which is more like a gradual thing, right? So we have replaced this kind of 0, 1 loss function with this kind of loss function, which is at least continuous. It is not still differentiable here, but at least continuous. This one was not even continuous, right? So instead of this 0, 1 loss function, we actually, with those slack variables, we are replacing this loss function with this. And what is this loss function? Our loss function now is max of 0, comma 1 minus yi w xi. What does this mean? This is essentially saying the same thing here. Okay, let's look at cases. Right? So this is essentially our EIs. What happens when this is 0? What is the loss? Loss is? Yeah, we are just trying to characterize this loss function, right? Okay, again, what is our best case? When epsilon is 0 and this dot product is actually greater than equals to 1. So if it is greater than 1 or greater than equals to 1, what does this function give us? 0. So if this axis is yi w xi, if this is 1, for all the points that are greater than equals to 1, your loss is 0. There is no loss. That basically means every point you have are maximally separated by gamma. Maximally separated by gamma. That means this, there is no loss. Okay. Now if it is exactly 1, still you have 0 loss because you are still on that line, margin line, maximum margin line. If it is less than 1, you are still correctly classifying. So for the region where yi wxi is between 0 and 1, what happens? Are we doing a correct classification or not? Is the classifier correct?
Yes.
Yes, because still we are greater than 0. But we are not very good. We could not achieve the maximum margin of greater than equals to 1 according to this formula. We are doing something okay, but not what we actually ideally want. So that's why there will be penalty. And that's what, and it's a linear penalty, right? If you do 1 minus this, that becomes a function like this. where if, let's say, this gives you 0. That's not a good thing, right? Because you're confused now. The dot product is 0. You don't even know like which class to assign. That's not good. So at that point, this function gives you 1, which is a loss of 1. Right? Things get even worse when you have a negative dot product. Because now you have a number here that is greater than or equals to 1. That is less than or equals to -1. Actually, as long as it is less than or equals to 0, we are good. That's a bad misclassification, right? So you will get something that is greater than or equals to 1 because minus a negative number, let's say minus x. So you will have 1 plus x. So your penalty becomes even higher linearly. Right? So with this formulation, what we are trying to do is essentially using a loss function like this to minimize these slack variables. Okay? Because we want these values to be greater than 1. If it is greater than 1, no loss. If it is less than 1, it will have a linear loss. Instead of using the 0, 1 loss function like this. Okay? So, this problem that you see here, we have talked about this for a while, right? You have minimization of two different things, the slack variables and the W square. With respect to these constraints, the nice thing about understanding these constraints and putting them as part of the objective function is you now have just one formula to take care of. So what this means is this function is essentially that function. And now you have just a single function, no constraint. I mean, the constraint is already encoded in the objective function itself. Because with that constraint, like optimizing that function with this constraint is essentially optimizing this function with no constraint. This is where the computer science will come. We'll eliminate those constraints and we'll get rid of quadratic programming. Any question on this formulation? See, we want to achieve this constraint. Instead of achieving, like treating them as constraint, we switch them to an objective that gives some loss if we don't follow this constraint. So we are transforming constraints into the objective function itself. And now we just have a single objective function that we need to optimize without a constraint. Essentially, we are encoding those original constraints. It's just part of the objective function itself. Because you can summarize all this constraint with this single function, which is the max of 0, 1 minus this. And this is a well-known loss term which is called a hinge loss. How many of you have heard about hinge loss? Just one? Okay. So this loss function is actually called a hinge loss function. And this form is more interpretable. You have less equations to worry about. There is no slack variable anymore. Everything is in terms of x, y, and w. That's something we already know. We know x is our data, we know y is our label, and we know w is the plane that we are trying to learn. And we have a single minimization problem in terms of w. Life is good? Is it really? Are we done? I mean, this is our loss function. We have just one loss function. We just want to optimize this, right? Then what is wrong?
Still got to worry about gamma.
Still got to worry about gamma? No, because we have taken care of gamma by doing w square. We don't have to worry about it. This minimization will make sure gamma is maximized. We are good there. What is the problem here? Okay, how do you minimize a function? What do you do?
Like one numeric, I mean, for like a numerical approach, you could just get sample points. I'm not really sure what you do a gradient.
No, think about, yes, so think about a closed form equation, x squared plus 2x plus 3. How do you optimize this function? How do you minimize it? What do you do?
You could, if you have the derivative, you can find the derivative.
You take the derivative.
Yeah.
That's the gradient, right? I mean, you compute the gradient. Can we compute the gradient here?
We don't know if it's different.
Do we not know?
Well, for the max function, the derivative is definitely not continuous.
Max. Well, max, maybe it's still continuous. It's
Okay.
just not differentiable.
The derivative isn't continuous.
Yes, yeah. So max function is not differentiable. That's the problem. I mean, we have a closed nice form solution and everything, but unfortunately that is not differentiable. So in order to apply gradient based techniques, now you cannot, which computer scientists and machine learning engineers love a lot. Compute gradients optimize. Right? Okay, so first of all, let's try to understand what is happening here. What are we trying to achieve? So the first part, the W square, is essentially about maximizing the margin, right? That's what we want, a maximum margin classifier. And the second part is actually making sure we are doing the correct classification. We either properly separate the data, or if we cannot, then we are minimizing the amount of error we are making when we decide on a plane. Right? These are the two things we are combining with a weight of C. And that's a kind of hyperparameter you have to play with in your data set. So there are three cases here. We already talked about this. What are the three cases? This dot product could be greater than 1. It could be between 0 and 1, or it could be less than 0, negative. It could be here, it could be here, or it could be here. If it is here, we are good, right? I mean, dot product is greater than or equals to 1. That's what we want. But things become problematic when the dot products are here, and we need to impose a penalty, right? So three cases. Example is correctly classified and is outside the margin. So you are separating it beyond gamma, that 1. Normalized gamma is 1, right? So your data point, if this is the classifier plane we learned, is actually on the other side, outside the margin, which is like this. Good. No loss. The second one, it is somewhere here. Right? Actually, it is somewhere here. Then we are doing a correct classification, but still we want to impose some penalty because you got so close. Think about this. You are driving a car, the speed limit is 70, you are on 65, you get a ticket. Hey, you are too close to the speed limit. It's not something that you would want, but that is like strict enforcement, right? Don't even get close to the speed limit. That's what we are trying to do. You had a question?
I was going to say we can probably do like we did for the distinct graph and throw an exponential in there.
We could.
Throw an exponential to estimate the function. You have e to the negative t. It kind of looks like the loss function.
It kind of looks like the hinge loss function. E to the power exponential looks something like this, right?
E to the,
You mean the other way around?
sorry, not the logistic function, but e to the negative x itself looks like the hinge loss function. It looks like a,
You mean like this?
yeah, kind
Yes?
of, except smoothed out.
Yes? That just doesn't give you a margin. Other than that, you are fine. Right? That's this one is all about ensuring the margin. Because you have this one is coming from the gamma, a normalization of gamma. So that is actually related to that gamma. Let me see, how are we doing with time? Okay, we have some time, so let me go over. And then if you correctly classify, so if you incorrectly classify, you get a margin, penalty. And if you correctly classify, but you are too close to the margin, you still get a penalty. That's what this part is. You correctly classified, but still get a penalty. And here you get like even bigger penalty because you are wrong. And this is what called the hinge function, hinge loss. Okay? So max of 0 and 1 minus the dot product, which looks essentially like this. You have the dot product in the x-axis. If the dot product is 0, that's the most ambiguous case. If dot product is greater than 0, you are doing a correct classification because you have a multiplication with y here. So this part is correct classification. This part is wrong classification. But even if you do a correct classification, but you are within that margin, maximum margin, you still get a penalty. You only get 0 penalty if your dot product is greater than 1, which is the maximum margin that you want. It is essentially saying this is greater than gamma. This part is ensuring you are doing greater than gamma. This part, you are doing greater than 0 but less than gamma. Some penalty. This part is kind of worst. Wrong prediction. More penalty. And the further you are in the negative domain, the more mistake you have made, the more correction you need to make. Higher the penalty. Right? So this is the hinge loss, and this is the 0-1 loss that I already showed you, right? If you make a misclassification, you get a misclassification count. This is just a counter function, which is not continuous, not differentiable, and which is hard to optimize. There is no closed form formula So we, instead of 0-1 loss, we prefer hinge loss. So if we ask you, what is wrong with 0-1 loss in SVM optimization, you should be able to answer. Right? All right. So we have talked about this. We have talked about this. We have shown this. So in general, what is happening? In general, look at this function a little more closely. This one. This one. This one. What does this term actually look like? Does it look familiar to what you have already studied before? Yes.
It's like regularization.
It looks like a regularizer. Isn't it? What kind of regularizer is it?
L2.
This is L2 norm. Is that correct? How many of you have never heard about regularization? This was part of your midterm exam, the first one. No? Or maybe not. It was part of your assignment number 5. Regularization. Assignment number 5. Right? Linear regression. We covered multiple regularization techniques. We talked about Euclidean functions, right? We talked about ridge regression. We talked about lasso regressions. And this is kind of the formula that ridge regression takes in. Remember? And that was a regularizer that was with respect to the L2 norm. So, long story short, I know you don't remember this. I can see from the faces. So go back home and read the regularization. For the next lecture, we'll need that. So this is essentially like a optimization function, objective loss function, with some kind of regularization on W square. What kind of regularization we are talking about here? This is essentially a circle, right, in 2D. So essentially we are saying, find me a W that has a smaller value. So I would prefer some W from this circle than some W from this circle. It's trying to shrink that circle. The smaller the magnitude of W is, the better it is, because that minimization of W is actually what guarantees maximization of gamma. That is what we have defined. So we are essentially searching through, we are using a regularizer, L2 norm regularizer, L2 regularizer, to find a solution that has a minimum magnitude in Euclidean space. Okay? So learning is basically your loss on the training data and the regularizer, because if you think about this doesn't even depend on the training data. This is what comes from the training data. This is just giving you more constraint in order to choose a particular solution from a set of solutions. And we choose this because we want to minimize W square, which actually means we want to maximize gamma, because this is a maximum margin problem, right? We want to maximize the margin. That's why we need this. So the first term is the regularization term. The second term is actually the empirical loss, our original traditional loss function that we talk about. And here our loss function is hinge loss. So SVM, estimation, is essentially a regularized L2 regularized hinge loss function. Okay? It's a L2 regularized hinge loss function. Essentially a hinge loss function where it is trying to find a W that has the minimum magnitude. And that concludes today's lecture. We will continue next Tuesday. So this Thursday there is no class. Happy Halloween.
Don't have class, you guys just.
98. 7. Sure. Wednesday at 3, right?